started that recording. Okay, so we're working through the exchanging data stuff, and the first, oh, here he is. The first few topics are to do with compression and encryption systems. So we'll start with compression. Some of this, chip in if you want to ask a question, but some of this is sort of a little bit of a retread of GCSE. The depth and the way that you answer the questions, though, is about the why and the how. Why do we use that system? Why don't we use that system for this sort of data, and etc., etc. Okay, so we'll start off with the compression stuff, and obviously there are two types of compression with these names that vaguely sound made up, and I do sympathize with you on that. Lossless compression and lossy compression. Okay, so let's talk about the lossless stuff first. I can't even say that very well. Lossless. Too many L's and S's. Okay, so it might. No, I can't. No, sorry. Right. So the key point about lossless compression is that we retain the original data. So when we decompress, we get back what we started with when we went through the compression system. So what you've got to think about is, under what circumstances is it that we want to try and reduce the size of something, but we don't want to lose any single bit of information. So in general, that's when we're talking about data files. So whatever those data files are, whether they're Word documents, spreadsheets, database files, code files for computer projects. So when we've got stuff like that, or where we've got applications and programs. So obviously, if we was to compress a program and we used some lossy method where we threw away a load of the data and a load of the code, we wouldn't be able to execute that code. When we decompressed it, it wouldn't work. All right, so the core thing is not necessarily what compression system, but what general method should we approach with different contexts. Okay, so there is no right answer or wrong answer, but there is an appropriate answer. So whenever we've got data or we've got programs, then we have to use lossless compressions, which systems like LZW, WinRAR formats, WinZip formats, 7-zip, they're all lossless compression systems. That's why they don't necessarily, depending on the type of program or the type of data, you don't get mega compression ratios. So that's one of the downsides to lossless compression, is that you don't achieve really good compression ratios. Oh, dang, people keep getting kicked today. So if you do get kicked, in fact, should I try and turn the lobby off? I don't know whether I can do it now the meeting's started. Let me just see if I can do that, because that was happening all the time this morning. Meeting, no, meeting details. I don't know whether it'll let me edit them though. I'll just checking. No, I can't edit it now. Right. So in future, I won't do that lobby thing. Because if it's going to keep kicking people and you have to keep waiting to be let back in, it's a bit rubbish, to be honest. Right. Okay. So yeah. So with lossless compression, benefit is we can reconstruct an original file, but it's always about the context. Don't just waffle about things like this. Always give an example. So let's say like a program is decompressed and all the instructions in that program are available. So you need to give a context. Right, so why do we do the compression? So the base quality of compression algorithms is they make files smaller, okay? But that's not why we compress things. The why we compress depends on what we're using that file for, and this is really important. So one thing that I didn't mention to the other class, so I'll add it onto this diagram. We compress files so we take up less storage space. That's one reason of why we would compress a file. Okay, so that's on our secondary storage device, and I think in most operating systems these days you can tell it to compress files. Okay, so you maximize storage space. What that means is every time that we open a file we have to decompress it, but actually the time to decompress versus the time to load it, you can decompress as the file is being loaded into memory. So it doesn't become a massive issue if we're talking about loading and saving files. Okay, if you're constantly editing something, yeah, that will be a problem. But if you're just like loading up a Word document and you work on it for a while and then you save it, then that wouldn't necessarily be a problem. So we can try and save space on disk. But really what we're trying to do, the base reason why we compress things, is to do with transmission time. Okay, so I am going to add to this storage space. I'm going to say use less space, but also enhance archives as well. So if you're saving, you're doing backups and things like that, one of the things that you might want to do is compress the backup data so it takes up less space on the backup media, on tape or the other disks or whatever you're using for that. Right, okay, so it's all about, for me, it's all about transmission time. So transmitting data. So the context is, where is the data stored and where is it going to? So one obvious one is loading something from a secondary storage device. Okay, so we want to load a file into main memory so that we can process the data in there, or we can execute the program. So if it's compressed, then obviously it won't take as long to transfer from the storage device to main memory. It needs to be decompressed, but what you'll find, and if you look at the latest consoles from Microsoft and Sony, both the PS5 and the Xbox Series X, they've got dedicated hardware that will do the decompression on the fly. So as the file's being read, it decompresses the data. Okay, so I'm going to add that in there as well. So you can get dedicated decompression. So that's what Sony are really using to make their limited storage there, because they're all using SSDs, but it's super expensive. So to reduce the amount of SSD they use, all assets, all the like textures and everything, are stored heavily compressed. But when they're loaded by the game, by the graphics card doesn't know they're compressed. It just sees the textures once they've gone through the decompression engine. So we can put that in so that you never really know. So it becomes an abstract thing. Storage is abstract anyway, but the compression becomes an abstract thing. It's just a file. The fact that it appears to us decompressed, we don't know what's happened to it before it got to us, and we don't care. We just say, right, that's the file we wanted. So yeah, you can get around the problem that files are compressed by having dedicated hardware. So it doesn't affect the CPU load, the GPU load, or anything. Okay, so that's one area where we're going to transmit data. But the other one, and the one that you mustn't get hooked on, is saying internet. What you mean is networks. So we're transmitting data across networks. So this this might be, if you're like some tech nerd, you might have a server at home, and you might have a media server, and you want to pull files to lots of different devices. So if they're all raw files, then you're going to overload your network. So if we can compress them, we reduce the bandwidth required to transmit them, which means you can transmit more actual data than necessarily that you got the bandwidth for. And you see this in streaming as well. Okay, but obviously that's not lossless compression when we do streaming. But yeah, so everything that you connect to a computer has got a communication channel. Your monitor has got a communication channel. So I'm currently on my computer here, I've got a 1080p laptop screen, I've got a 1080p second monitor, and I've got a 4K monitor. Now that means that my poor computer graphics hardware is having to spit 60 Hz 4K data to one monitor, 1080p data to two other monitors, and they're all separate bits of data. So that's a hell of a lot of data that's being transmitted every second, okay, because they're all running at 60 Hz. So actually the HDMI data is not raw data, it's actually compressed. Okay, so there are codecs involved in transmitting this. Otherwise, you just saturate the bandwidth that you've got. Okay, so one of the other things is we keep having things that are more data resource hungry. So we're currently, people are starting to get 4K tellies, not that there's any content for them, but now 8K tellies are getting pushed towards us. And there are 16K tellies. So they keep quadrupling the resolution, the number of pixels. And they're having to keep inventing new codecs to keep the bandwidth down. But these are the sort of things, these are the sort of media, when we're talking about images, video, audio, that we're not talking about lossless compression. Okay, we don't tend to use lossless compression with media, because media has got a lot of content and lossless wouldn't give as much compression. Okay, so there are specific areas where we use lossless compression, and we're going to look at a couple of those in a minute, but video and audio are not two of the areas where we use lossless compression. Okay, so it's all about context. It's all about what am I trying to do, and what's the best system to use. Okay, so if you get a question about this, there have been questions where they've talked about lossy versus lossless, and they've said discuss, and so obviously you've got to put scenarios down, and you've got to give the arguments and counter arguments for these things. Okay, so lossless compression, it will compress things, but it's not necessarily going to give you high compression ratios. There are two standard methods of doing lossless compression. One is run length encoding, which has the acronym RLE, and the other one is to use something called dictionaries. Okay, so we're going to come back to those in a minute and look at those specifically, the process that they work. There was a question once that got you to compare run length encoding and dictionaries with, and they gave you a little task and said, right, we'll talk about the pros and cons of both. So we do need to know roughly how they work. The specification guidance says you need to be able to actually maybe process some text and do a dictionary. But I'm not going to worry about that now. That's beyond the realms of time for doing what we've got to do. So let's have a look at lossy compression. Anyone got any questions about lossless to start with? And then I'll move on to lossy, and then we'll come back to run length encoding and dictionaries. Right. Okay, so lossy compression. Okay, now the key thing with lossy is that we throw data away, and that's how we get. Now you must never ever say you remove quality. What we're saying is we're discarding information so that we can get high compression ratios, and you can get ratios 100 to 1, so you can get down to 1% of the original. depending on how brutal you discard. Now, you can't say that you're reducing quality because it's stuff you can't hear and stuff you can't see. Okay, because generally we use lossy methods with constant media, so like video or audio, where we're constantly being delivered new information. Okay, but you must never say, weirdly, that you're doing it because you can't tell the difference. Okay, it's not about that. It's about what's acceptable quality wise with the scenario that we've got. Okay, so if you're watching video on a phone, for instance, so I've got my phone here, the screen is high resolution, but if you, I mean, this screen can do 4K video, but really, 4K video, I probably wouldn't be able to tell the difference between 1080p and 720p on a phone screen. Okay, so you start having to think a little bit clever, and you go, you know what? If I'm watching a YouTube video and I've held my phone in portrait mode and the screen is just taking up the top third, there is no point in having full 4K video. So I can go with a lower resolution. So it's all about what can we do in order to remove some content. So with images and video, one thing, specifically images, one thing you can do is you can change resolution. So you then need to think about under what circumstances is it okay to take an image and compress it and drop the resolution in order to be able to show the image, but not really care. So your classic example of that is like previews on web pages, thumbnails, where we don't need the original resolution. You just need a representation of the image. Okay, so you can change resolution. You can drop it. You don't want to increase it because we're trying to compress. Okay. The other thing you can do, and again, this is some of these things we've discussed at GCSE. You can drop the color depth. So in a standard photo format, we store 24-bit color, 16 million colors, which gives us the color gamut so that we can get close to representing the colors that our eyes can discern. Okay, so I think the human eye can discern about 1 million different color variations, but in order for us to deliver, we don't get close to that, but in order to get close to 1 million, we need to be able to store 16 million colors. Now, there's a bit of convenience here because that gives us 1 byte per color channel. So we have 256 values of red, 256 values of blue, and 256 values of green. Okay, if you look at new color formats, so like UHD, okay, so this dynamic color range formats that we've got, they're 10 bits per pixel per channel. So in terms, if you've got like a high dynamic range image, you've got 30 bits for every pixel. So one of the things you could look at is saying, well, do I need that entire range of color? Should I reduce it? So when you're looking at streaming services, there is no point if your stream isn't got the bandwidth, there's no point in trying to transmit high dynamic range color. Drop it straight away, go back to 24-bit color. So you'll automatically get a compression. So the compression algorithms, they do make things smaller, but they're also there to like take data away. Once that data is gone, you can't get it back. Okay? There's no way you can manufacture data that has not been transmitted, which is why we can't use these lossy methods for data like programs and important data files. Okay, so we can't reconstruct. So you mustn't ever suggest lossy methods for code or for data. Okay, you can't like have two or three out of every 5 pieces of data in a spreadsheet not there. It just wouldn't work. Okay. Now there have been quite a lot of work, and it's starting to come into fruition with compute units and graphics cards and things. Systems that can interpolate. Now you may have heard of this, where people temporal resolution increasing systems and aliasing systems. I think one of the NVIDIA ones is called DLSS. I can't remember what it stands for. But they're like machine learning systems that can take data and they can try and interpolate through machine learning training. They can interpolate what would have been in the image. So you can work at a lower resolution, which means you've got less bandwidth, less texture bandwidth, you've got less information that you've got to move around from primary storage to graphics storage, secondary storage, all that sort of stuff. So you get all these knock-on benefits, but then these systems can sort of like fill in the gaps. Okay, they're not perfect, but people have done tests and they can show that at certain resolutions you can't really tell much of a difference. So these sort of things are becoming more and more common, and there's a big push because it allows us to compress more, okay, and reduce bandwidth, because bandwidth, especially in graphics stuff, is like the limiting factor on a lot of video effects. So how fast can we move data around? Okay, so if you can send less data and then use some clever systems in the back end to try and interpolate, but it only works with this sort of stuff where we do not need it to be exact. Okay, it's really no good for anything other than streaming media of whatever format. Remember, streaming is a funny term. We think of the internet, but actually we're streaming all the time. Okay, so I'm recording this. That's being streamed from RAM, from the graphics buffer, to a file, which is why my computer fan is going like Billy-O, because the CPU's murdering itself, because I'm also doing capture. I'm capturing and recording, and we're transmitting on the internet. So there's a hell of a lot of data being transmitted by my poor laptop at the minute, which is currently cooking itself. Okay, so when we say streaming, we don't just mean on the internet. It's a bit like the old GCSE meme, isn't it, of Wi-Fi is not the internet, which all the students seem to put. Okay, so there are various codecs. So these codecs are responsible for removing some of the data, packaging the data up ready for decoding later on. So you've got your classic ones, your H.264, which is our high definition ones. There are other variants of that that are coming along to do UHD and to do 8K video. There is a brand new one that's been out about a year that is really good for compressing high definition, high dynamic range content. But again, it is throwing stuff away, and you can see if you go on digital telly, you'll see lots of artifacts where they've over compressed and they've thrown so much information away from the video frame that you sort of get these horrible averagings, and that's sort of how the compression systems work in video. You get these transforms that take averages from pixels, so that when they come to reconstruct, they go, it's just blancmange colour, and you get like a big area of blancmange, and you can see it particularly bad on scrolling ticker tape things on news feed. You can see all the blockiness behind it, where because you've got constant change in video, you get that blocky, and you see it in films in dark scenes. If you've got a dark scene and something bright goes across, you get a horrible ghosting effect. And it really doesn't matter how good your post-processing is on your TV. You can't eliminate that ghosting effect because it's inherent from the compression algorithm. Okay. So there are loads and loads and loads of video codecs, and the reason there are loads is because they're all suitable for different types of scenarios. You haven't got to know any specific ones, but you've got to know that there are limitations on video. There are audio codecs, MP3, AAC, FLAC. There's quite a few different ones for that as well. And again, some are better than others. MP3 is pretty poor quality. I knew it was the beginning of the end when MP3s came out and people started accepting MP3 quality audio. And I thought, well, there you go. We're going down to the lowest common denominator here. Nobody cares about quality of sound anymore. We might as well not have ears or something. I don't know. So you've got to be careful with things like that. Right. Any questions about lossless? It's all context. It's all context. No. Are you all still here? Because that would be handy. Yeah, we're here. Are you all awake? More or less. Right, okay. Right, let's have a look at run length encoding then. So, at its heart, all run length encoding is a bean counting system. So we can use run length encoding for lots of different things, but one of the best uses for it is low color images, which CompuServe, a guy working at CompuServe, I can't remember his name now, but a guy working at CompuServe came up with a GIF format, spelt with a G, just to make sure that everyone called it GIF instead of GIF, so that he could get annoyed. And he does get annoyed. If you ever meet him, find out what his name is. If you ever meet him, say, oh, thanks for the GIF format, and you'll annoy him. He might punch you in the face, I don't know. He gets quite annoyed. But he should have spelt it with a J if he wanted it to be called GIF. But there you go. Right, so what this does is it counts runs of pixels of the same colour. So instead of storing every individual pixel's colour, okay, what we do is just say, oh, look, we've got a colour and there are 10 of them in sequence. So instead of storing 10 pixels, we go, well, it's this colour, this single colour, and then you just repeat when you decompress 10. Just draw me 10 pixels. Okay, so we're making use, and what's really nice about it is we're making use of the way that we actually draw graphics. We draw graphics in horizontal lines, raster images. Okay, so as you're reading the data, you can read it and say, oh, I've got 50 black pixels. So put it on black, draw 50 black pixels. What's the next bit of data? And it's quite a good system to make use of the way that images are drawn. Okay, because you tend to, that's how you draw images. Right, so if we look at this is a line from a picture. Okay, so I've got a couple of red pixels, and then I've got a few blue pixels, and then I've got some green pixels. I noticed Richard's not chipping in and telling me they don't look like pixels or anything like that. So he's obviously asleep. Joined late, he's probably getting out of bed. He's probably still in bed, to be honest. Shut up, bold. I can't read that, Richard. Actually, I'm blind. Actually, shut up, bold. Shut up, bold. Oh, okay. It's nice, isn't it? Right. So, in this scenario, we're gonna assume we're using, because this is what GIF format uses, 256 different colours. So we can store each pixel's colour information in a single byte. Okay, so if we was to store this fragment of this image raw, it would take 13 bytes. But using run length encoding, what we can do is we can record the colour value once, and that just takes a byte. Okay, so we're not increasing the number of colours or anything, we're just saying, right, okay, that's a byte. And then we have another counter. So we follow that with a counter. And we say, in this case for the red one, 2. So actually, we haven't got any save in there. It took up 2 bytes before, and now it's taking up 2 bytes. So there's no save in there. But once we get onto the blue one, there are 7 blue pixels. So we record blue in a single byte, and then we use 1 more byte to say there are 7. So actually, instead of using 7 bytes, we've only used 2. And then we get a similar saving with the green one. So overall, to record the 13 bytes of information, it only takes us 6 bytes. So we call it compression, but we're not actually squeezing anything. What we're doing is we're analyzing a block of data and we're saying, how else can I store that data? It's actually a different storage mechanism, okay, which we just call that compression because of its effect. We call it compression because it has an effect that makes things smaller, okay. But there is always the possibility that the data that you're compressing with the algorithm that you're using can force a file to inflate, and then the compression is useless, or that form is useless. So if you look at the next fragment of image, I've got alternating pixel colors. So I go red, blue, green, blue. Now you'll get this sort of effect in an image that's stippled. So like where you've deliberately changed colors every pixel to get an effect, or in a photo image where generally every pixel will have a slightly different color. And this is where run length encoding breaks down completely. Okay, it doesn't really work with busy, noisy images. Okay, so if you've actually got an image and it's, let's say you had a picture on a camera that had a very bad CCD, the sensor that takes the image, and it introduced a lot of noise, you'd have a lot of stippling that you might not necessarily see, but when you look at the data, you'll see there's variations. Okay, so you may have images like that, especially when you zoom in. When you use digital zooms and things like that on cameras, you do start getting more noise the more you zoom. Okay, so when we get in that situation, if we're going to use the same system, you can see that these 6 pixels will take up 6 bytes because that's the raw data. But if we then go with a run length encoding, it's actually costing us 2 bytes to record each pixel because we have to still say the color and then we have to say the count. Okay, so we get red and then there's one of them, so that's 2 bytes. So actually, if we use run length encoding on an image that's not suitable, that isn't got blocks of color, then we'll get an inflation problem, which is no good. Okay, so that's where you would say, right, well, run length encoding is no good for that type of image. So if you ever really look at GIFs, it's quite funny because they've sort of been hijacked GIFs into making mini video clips, but it wasn't their original intention. They were for storing 256 color images, and a lot of the times there were 64 color images and 128 color images, and they tended to be like posterized, so they had big blocks of color. Okay, so whether you get any decent compression on all these animated GIF video clips, I don't know. The quality is usually pretty rough, all right, to allow it to get some sort of compression, but that they were never meant for video clip storage. Okay, they're more for like poster, because they were used for advertising banners and things like that. And in fact, Flash, bless its soul, which is getting finally gone. Oh, what am I doing with the zoom on this? Flash, which is going finally after in its death throes for 10 years, that used run length encoding as well to encode all its stuff. Because again, that was flat, lots of flat color in animations and things. Yeah, I mean, it should have gone years ago. Flash was great until Adobe bought Macromedia in 2004, 2005, and then that was the end for it because they never fixed all the bugs. They just kept introducing features like a lot of companies do, and just leaving bugs. And then that was security problems, and everyone was like, "Ooh, don't want that anymore." So it's a victim of itself, to be honest. It was very nice, Flash, quite nice to program, to be honest. You could do some real weird tricks with it. But anyway, right, so run length encoding has its uses. The GIF is one good example, so low color images, but not where you've got lots of variation in color. It does not like that at all. Okay, so another task that we might want to do is compress text. Okay, so here's a little phrase: the cat sat on the mat. Why, we don't know. Maybe the cat is sad or likes a good mat. Okay, so that just came out of my head, like everything does. And I want to try and compress it. So we could try run length encoding, but there really aren't. I don't think there is anything in here where I have got. Oh no, I do tell a lie. Where we've got good, we have got 2 consecutive characters. But that, I think, is the only place. Okay. What you can try and do is look to see where you've got pairs of characters. So if I could do it in character pairs and say, all right, how many times does TH appear? Well, once. AT, and then I got AT again, AT again. So there are things that we can do, but run length encoding is not going to work very well for compressing text. Because, there's, again, like the stippling of a graphic, too many variations, too many changes. Okay. One thing you could do to try and compress text is reduce the character set. Okay. So just use capital letters. If you use just capital letters, you can get down to 5 bits, which will leave you a few characters to do punctuation, etc., etc. And then you could start looking at other methods of compressing that data. Okay. But there is one method, another lossless method called dictionary encoding. Now, what this attempts to do is record data items once. So where you've got repeating information, instead of keep repeating it, you say, well, hang on a minute. Let's build a dictionary of all these items and then have that as metadata to the file. And then to actually encode all those items, let's just use an index. Okay. The problem with dictionary encoding is it works better as data sizes get bigger. So if you try and do this with this small phrase, you'll see that we can get compression, but it would be better if the text was bigger. I don't mean physically bigger, like, I mean there's more of it. Okay, so the more often we repeat words, the better the compression will be. So there is a cost to storing a dictionary, and there's a cost to storing the references that make up the original text. Okay, now it takes time to process this data, but often you'll use dictionaries in a situation where you've got static data. So if you wanted to compress a book, okay, you compress it once and then store it in its compressed format, and then when we decompress it is when we want to read it. So we load it, decompress. Okay, so it doesn't matter that it might have taken an hour to encode the book, because it's the decompression that matters, and that's quick. Okay, so here we got our phrase. Now in total, if I assume that I'm using 1 byte per character, including spaces, then what I've got is about 78 bytes. I might have sort of added this up wrong a little bit, but let's assume it's 78 bytes. Now what we would do to process this passage is we would take every word, and the first time we see it, we would add it to a dictionary. So this is a real rough one. Okay, it's got 16 slots because there are 16 unique words. The one thing I don't have to store is the spaces, because when I decompress this, I will automatically put a space in between the words. Now I'm simplifying this a little bit just to get over the point, but it's things like that where I've got data that doesn't actually mean anything. It's a visual aid for the user. Okay, a bit like when we write postcodes, we put a space after the first 2 letters and first 2 numbers, and then leave a space and then put something else. A bit like when telephone numbers, we tend to leave spaces. So we put the area code or the connection code and then the number. Okay, but we don't have to. That's a visual thing. So the spaces between words are visual. Okay, if we were decompressing this to speak, the pauses in between words are an audio cue. All right, So we do not need to store everything. So we get a little bit of benefit there. But this is essentially how the dictionary works. So the phrase that we originally had, once we've encoded all the dictionary items, would actually be 0, 1, 2, 3, 0, 4, 5, 6, 7, 8, 9, 0, 1, 10, 11, 12, 13, 14, 15, 4. Okay. Now all those are our references. So all we've got to do to reconstruct the phrase is to use these as indexes to this table, this dictionary. So the looking up process, the decompression, is super quick because it is just a matter of going dictionary at position 0, dictionary at position 4, etc. Okay. In fact, interestingly on this one, because there's only 16 unique words, you wouldn't need to use an entire byte to encode this. You could use nibbles. So you could have every nibble. Okay, and process and store two words in every single byte. So we actually compress this down to 10 bytes. Okay, and actually there's nothing to stop you taking the dictionary and applying a compression algorithm to the dictionary and taking the actual phrase references and compressing that down as well. So there can be statistical things that you can spot that would allow you to compress these individual items even further on top of the dictionary format. Okay, so again, you've got the problem if you've got passages of text where there are lots and lots of unique words, or there are lots of short words. So you can see in this one I've got lots of short words. If I've got lots of different short words, then I'm not going to get much compression benefit, because let's just pick one. I've got likes there, which is a 5-letter word, so it's taking up 5 spaces in the dictionary, and then actually to use it I have to have a reference as well. So actually to mention the word likes takes up 1 extra byte than what it did on its own. But dictionaries are great for things that repeat and are used often. Okay. Now, one of the problems with dictionaries is finding if something's in the dictionary. So if you was to use the system that I've used here to search to see if a word's already been entered, so when I get to Matt at the very end, I've got to search through, but they're not in order. So we end up stuck in a linear search problem. Okay, so as this dictionary grows, it's going to take longer and longer to see if there is an entry for a word in the dictionary. So there are loads of things we can do. I'm not going to go deep into any of this, but obviously you could store the dictionary in order using some sort of tree system. Okay, so you get the benefits of the linked list mechanism, but we organize it as a tree so we can keep it alphabetically ordered or something like that. Okay, so you can narrow the search system down, but the better system, and the system that works very well with dictionaries, is hash tables and hashing algorithms. Okay, so just a reminder of hashing. We generate a key. So in this case, for this Word document, we would take the words and we would hash them and generate a location to store. Remember, that's what the hash tables are. It gives me the location where I'm going to store something. Okay. So the lookup process is quick because all you do is you apply the hashing algorithm. There's no searching involved, and we can see if there's nothing at that location, the thing doesn't exist. If there is, if it's the thing we're looking for, then obviously it's been done already. Then we can forget. Remember, there's one big problem with hashing, and that's collisions. Okay. We need to deal with collisions, and there are those 2 methods. Remember, we have got the next available position method, where we just like look for a space down from where we wanted to store, but we couldn't because something was already there, which is rubbish. That's the rubbish system because it can knock other things out of their place. The preferred method is the list, the linked list. So we say, let's make a linked list of all the key values that generate the same hash. Now, depending on how well you created your hashing algorithm, you would minimize or extend those collisions. Ideally, you don't want more than 1 or 2 collisions, because that'll make the linked list quick to search then. If it starts getting long, you end up with a linear search, which is not good. Okay, so hashing algorithms are brilliant for dictionaries. I wonder what that red thing was. Sync status error. It keeps coming up, so I don't know what's happening with that. Probably going to get kicked out of the meeting or something. Right, so the hashing algorithm is really, really good in conjunction with a dictionary. And I think Microsoft's own dictionary object class uses hashing as the method of storing the data items. Okay. Right, other uses of hashing. And this is the last bit I want to do before I stop boring you to death. Right, another topic that we have got to go over, compilers and the process of compiling from source code to object code and machine code. Symbol table. The symbol table, a system where we want to be able to look things up quick. We're not going to search, we want to be able to look up. Okay, so everything that we write in our source code, keywords, the identifiers that are from libraries we're using, the identifiers that we come up with for our own code, they all end up in a symbol table. Constants end up in a symbol table. Okay, all the things that we code ends up in a symbol table, and the reason it goes in a symbol table is because the compiler wants to be able to check. Okay, it wants to be able to look up my name in the symbol table and work out what data type is it suitable to use as a parameter for this function, is the operation that's being performed on it legal, what static polymorphism do I need to use because I've got 2 different data types and I'm trying to do something called a method, but there's a few different method signatures. So the compiler spends a lot of its time looking things up in the symbol table. So hashing is a perfect use case. Okay, we do still have the collision problem, but what we do with languages is we pre-hash all the keywords. So the words that we know we're going to see, like if, while, function, then, and other keywords. So where you've got like class, static, public, private, protected. All these we know we're going to encounter. So what we do is we pre-hash them so that they definitely end up at the correct location. If I use something that generates the same hash location as public, then I'll go into the overflow. My thing will go into the overflow. So it will not slow the compiler down when it's hitting language keywords. All right. So we can do pre-hashing. There are a load of other things that we can do as well, other than hashing for dictionaries, but I might talk about those another time in the future when we're reviewing some of these topics later on as well. Right, and then the final one that I want to talk to you about is one-way encryption. So using a hash for one-way encryption. Now, what do we mean by one-way encryption? We mean where you can't actually, once you've encrypted the data, you can't get the original data back. That's what I mean by one-way. This is perfect for passwords. If only we could get these stupid companies on the internet to make sure that they hash all the passwords using a decent hashing algorithm so that no one can reverse them. Instead of them telling us, we've been hacked and they've got your passwords, they should be saying, we've been hacked, but don't worry, they're all hashed and no one can read them back. So you don't need to reset all your passwords on everything. But no one ever seems to say that, which worries me quite a lot. So passwords is a great example of using a hash. And the way that it works is we don't actually ever store the user's password. When a user logs in, what they do is they type their password in, the browser hashes it, and then you compare the hash with the hash that's on file and say, oh yeah, they match. Now, it doesn't need to be perfect, the hashing algorithm for this. You can have the odd collision, as long as you don't get too many collisions. You know, if someone puts the password is Prince Charles, and I can get the same password by saying on the keyboard, then that would be a rubbish hashing algorithm for this situation. But as long as, you know, the variance is such that only on a few occasions do you get duplicate hashes, it doesn't really matter. But someone would still have to try and guess that. Okay. Now, another use of this exact same one-way encryption system is for PIN numbers, bank card details, those sort of PIN numbers. Now, in an ideal world, this is what banks use. So if you forget your PIN number, if your bank says, sorry, we cannot tell you what your PIN number is, that means they're hashing, because they can't look it up. Even if they could open the file, which they probably can for maintenance, they could open the file, but they would not be able to work out what the PIN numbers were from that. Okay. If your bank says they will send you your PIN number in the post, they're not hashing. That is not a secure PIN. And my bank that I use, I won't tell you what bank I'm in, but my bank, they have to like reset. And it's the same thing online. If you're, say you forgot your password and they send you your password, so like basically all the things you log in for school accounts is like that, that means they've got your passwords in plain text. Okay. Any system that can send you your password is not secure. If they have to get you to reset your password, which is what all the decent systems do, then they are obviously encoding, they're hashing all the passwords. Okay, so say to yourself, next time you forget a password, if you get sent your password, that ain't secure. And be wary if you use that password on other systems. Okay, right, okay, I don't want to go any further with that. In the lesson on Thursday, going to get out of sync with the other class, but in the lesson on Thursday, we're going to do asymmetric and symmetric encryption, which is not one-way encryption, by the way. But what I want you to do for the next lesson, I want you to find out, and you can have a go at doing that now. You've got, I don't know if I can see the time. You've got about half hour left, or choose to use your time now you want. But I want you to try and find some more uses of hashing other than symbol tables, one-way encryption, and to work effectively as the dictionary creator for a dictionary encoding system. I want you to look at other ways in which we can compress text instead of using just dictionaries. Are there other methods? And I want you to look for, are there any other formats of data other than video, audio, and images that we would use lossy compression with? Okay, so just those three things. I'll save a reference list. I didn't think I added much actually. I think it was just that little bit I said at the start. You got the video anyway. So there is a reference to this in the B block class. So I'll link it again on the end of this chat for this lesson. Oh, my throat's going. Something chronic. So if anyone's got any questions, please ask. So for next lesson, we'll go through what you found out, and then we'll have a look at asymmetric and symmetric encryption. And then if anyone's got any, either on Thursday, if anyone's got either any queries about the project, or they've got their project documentation into a state where they want me to give them some feedback, then I'll gladly take that direction, assuming you've got it all linked up. I think we sorted all that last time. I think I've got a few problems in the other class, but I think you lot are pretty good. Got it all linked. Okay, anyone got any questions? No. Right. Well, I've done the register, ladies and gents. So I'll link that now. If you make sure that you have got that info for Thursday's lesson, then that'll be fantastic. One thing I will say, when I link this SVG in a browser, it doesn't want to show it at the proper resolution from the file. I don't know why, but if you download it and then open it in Chrome from your file storage, it'll show you at maximum resolution. So I don't know why it does that, but it's just a bit weird. Okay, so I'll add that to the end of the chat. Where are we? No, you don't have to submit it. You write it down in whatever format you want, because we'll just chat about it, and we'll get the microphones on and get you to, and we'll have a bit of a chat, as much as we can have a chat using these systems. Okay, right. So I'm going to try and I'll attach that to here. Oh God, got to find the window I've got it saved on. Should be on Edge somewhere. There it is. Right. Let me find it and put my glasses back on. Compression, and it must be that one. Right. Share. I'm talking to myself, I know that. That's what I spend most of my life doing. Don't really bother me. Right. So back to the team. Right. So it's in SVG format, which is like a vector scalable format, a web one, which is why it's weird that it doesn't show properly in Chrome and everything. I think one Teams must have something weird with the shortcut, but download it if you want to look at it fully. So I'm just putting this in the chat. Right, I've just linked that in the chat. So you should be able to open it, and it'll look. I'll show you what it looks like. I'll just drag this onto my main screen. Oh, everything's so slow. It's still opening it. It's only 6 meg. Right, so that's what it looks like. You can zoom it in and you can read it, but it's a bit iffy. It's better. That might be easy enough to see, but if you download it and then open it, then it's a lot better. It doesn't even give you scale controls. It's really weird. Okay, so yeah, so it comes up like that. So that's a bit awful. You can at least see the colour. So they're using some heavy compression on that. I don't know why. Seems like it's an SVG. But there you go. It opens better in Chrome, to be honest. Okay, so if no questions, just do those next lesson bits, and I will see you on Thursday. Thank you very much. I'll leave the chat open. I'll leave the meeting open for 30 minutes, but I'm going to leave you to it now. So if you want to sign out, sign out. If you just want to come and ask a question, just go to the chat and just ask a question on the chat. Okay, gents, ladies.